So imagine I have a shock wave, right? And so this is my u, this is x. Not all shock waves are stationary in any frame of reference. In general, shock waves just moves towards one side or another. So in finite volume scheme, it actually matters which way a shock goes. Because let's imagine the shock actually sits, the best scenario is when the shock actually sits just on the interface of two cells. So this is x, let's say I plus half. Ooh, what happens? Oh, okay, so let's say this is xi plus half, this is xi minus half, this is xi plus 1.5. Okay, so the shock sits exactly at xi plus half. So the question is, what fi plus half should be? Okay. Well, here, because I have a discontinuity here, my left cell value, which is ui, and right cell value ui plus 1 can be very different, right? So if ui and ui plus 1 are very different, then if I evaluate the flux function at ui, or if I evaluate the function at ui plus 1, or if I evaluate the flux function at the average of them, or if I just average the flux, all four of them are very different. You agree? Right? So when the shock wave happens, it's if the solution is locally smooth, then ui and ui plus 1 are very similar, then it doesn't really matter that much if I take any of these. It matters a little bit to my accuracy, but like not greatly. But if there is a shock wave, which one do I take actually matters a lot. It can actually affect if my solution is correct or wrong. So how do I choose which one to use? What is the physically correct flux to use? I mean, which flux actually determines, I mean, remember what is flux, right? Flux at this point is the rate at which the conserved quantity is from here is going into its neighboring control volume. F of ui plus 1, your choice is this. Why?
Because it's a discontinuity, it jumps down to the average.
I agree. The average, these two, okay, so these two, the average actually doesn't mean much over here. That actually, I agree. Right? Yeah?
Because if we're thinking about the flux that's acting at this point, it would be the previous one, and how it continue after that one would be the ui plus 1. But if we're talking about flux, whatever is after ending at this point, so I think previous one would make more sense.
Yeah, you think previous one is making more sense. You think the after one is making more sense.
Yeah, that.
Okay, so it seems everybody agree these averages are not correct. Yeah?
Does it depend on your time integration scheme?
Does it depend on my time integration scheme?
Yeah.
Why?
Does it matter like how you discretize the ODEs? Whether you're picking the one from this step or the next step?
Right, okay. I think you are starting to think about time. That's actually a very good thought. Right? So what actually happens at the next instant?
You have the full UI as
What?
flux.
You have the full UI. Why?
Because now the shock is like completely crossed the point, so it's not ambiguous what's happening anymore.
Okay, so yeah, you have a good point. So if at the very next instant, the shock moves past this discontinuity, and then at the interface, the value of the solution is actually ui, right? Then I should take the ui value. Is that always the case?
Then the shock may not be moving the way you think it is.
The shock may actually not move towards the right. Who said the shock has to move towards the right?
That depends on which way it's moving.
Yeah, it depends on which way it is moving, right? So both of your answers are correct, you should either take f of ui or f of ui plus 1, depending on this, which way shock is moving. If the shock is...
When you have a graph that looks like this,
Hmm?
when you have a graph that looks like this, doesn't that mean...
Does that mean the shock is always moving towards that side? Not necessarily. Let me find the example. Okay, just to think of the traffic flow case, right? Let's think this is the density of the cars. No, that's actually still moving towards that direction.
I can't think of an example where this exact graph would show the opposite.
Right. So, okay, think of a what? Think of the starting of a. You guys all know how does a supersonic wind tunnel works? Think of the starting of a supersonic wind tunnel. Okay, so initially within the whole wind tunnel, the flow is subsonic, right? Because it starts at rest, and then you have to have a very high pressure. You have to flux all these subsonic flow out. At some point, there is a shock wave forming, right? Downstream of the shock wave, you have what?
You have subsonic flow.
Downstream of the shock wave, you have subsonic flow, right? Upstream of the shock wave, you have supersonic flow. Actually, that's again moving towards the downstream direction. Let me see. Okay, then you have to think about the onstart of a supersonic wind tunnel.
Flow separation in the rocket nozzle.
Yeah, right, something like that. So basically you have a supersonic region, you have a subsonic region. The shock wave is moving backwards, right? The supersonic region receding. Right? Does it make sense? So that's the case when the shock wave is moving backwards. So it all depends on if your frame of reference is moving faster or slower than the speed of the shock wave. All right.
But if the direction was this way, we choose F through I not right.
Pardon?
If the direction was to the right, then we choose F through I not F through I plus 1, right?
If the direction is moving towards the right, you should choose UI. If the shock is moving towards the left, you should choose UI plus 1, right? It all depends. So how do we know which way a shock would go?
To know something about what the system you're modeling is.
Assuming you know the differential equation, right? So the only thing that determines what differential equation is the form of f. Okay, so it turns out that's actually which way the shock would go is a very tricky question. I mean, it's not so tricky if f is a single function, u, the conserved quantity, is a single quantity, right? So it turns out you can do a conservation analysis, say, and you can pretty much easily. So basically, you do a control volume analysis within a very small volume, just encompassing the shock wave, and you can figure out that the speed of shock is equal to delta f over delta u, right? So basically, delta f is f of ui plus 1 minus f of ui divided by ui plus 1 minus ui, right? So this is the speed of the shock. It's kind of a generalization to df du, right? df du in the smooth region of the differential equation is called what? Going back to this df du is the slope of the characteristic, right? So the slope of the characteristic in the smooth region of the solution, when generalized to a finite delta f over a finite delta u, is actually the speed of the shock. So you can basically look at is f of ui larger or f of ui plus 1 is larger, and divide by if ui is larger or delta ui is larger. You can figure out if the shock is moving towards the left or towards the right for a scalar equation. And then you can choose, should I use f of ui or f of ui plus 1? It's a little bit of a simplified version. In reality, there is also a case where the shock wave is going to disappear at the next instant, forming a verification wave. But like, if that doesn't happen, you just choose this or this, depending on the sign of this speed of the shock.